Example 1.4. 100 grams of helium gas is taken through a cyclic process shown in the figure. A. Explain the thermal process physically of what happens on the PV diagram. Calculate all the pressures, volumes, and temperatures for all three states. So here we're going to assume monatomic helium gas. As a side note, helium is extremely rare on Earth, but it is the second most abundant atom in the universe. Okay. There are two ways to transfer energy into or out of the gas. That's either by heating or working. So when we say that we do heating and working, so all heatings and workings of an ideal gas only increase or decrease kinetic energy of the gas particles. So when you look at that situation, you got to remember, so if we say that we increase energy, that means that the ideal gas, we have faster moving gas particles. If we say we're decreasing energy or that we decrease energy, then that means that these gas particles are now slower moving. So when we start to interpret this as to what is actually happening, you got to remember that that's what's actually going on. Okay, so now we want to go and explain the thermal process here. So then the question is that how does heating / working from the environment change the thermal state of the gas inside the piston? Okay. So the only way this can happen here is that we got to look at one process at a time. So the first thing that we're going to do here is that we're going to go from state 1 to state 2. And so let's add a picture of what this means here. So I'm going to go from state 1 to 2. So, and because this is happening at constant pressure, this is called isobaric cooling, and there's a compression that goes on. So let's focus on that. So there's two words here. There's compression and there's cooling. So when I say the word compression, what this implies here is that gas particles collide with the piston head. And then what you find here is that the piston head does work to increase kinetic energy of the gas particles. So what's happening here is that when I look at my PV diagram, it goes like this. So I'm going to go from this spot, from this spot, 1 to here. So if I look at this guy, I'm along this path right here. So what do I see here? I have a piston. So here's my piston. And what I'm doing here is that I am compressing my piston. So my piston head starts off here, and then it moves down to here. There's a compression because you could see that this is volume 2, this is volume 1, and you could see that there's a decrease in volume. So if I look at that, I could then see here that I am compressing. So if I make my gas be yellow here, then what is the piston head doing? The piston head is doing what? It's moving downwards. And as it moves downwards, it does positive work on the gas molecules, and therefore they increase kinetic energy. Now, what does cooling mean? So when I say the word cooling, you got to think about the gas particles. Cooling implies that the gas particles are made to decrease their kinetic energies. So therefore, that means that energy must be transferred out of the piston. So the only way that I could take energy out of the system is that I need to have something that's going to be cooler. So now what you're seeing here is that what I'm going to do here is that now I'm going to make this a cold bath here. And so as a consequence, then that heat now flows out. So then when I look at my system, I'm seeing that I have heat that comes out of the gas. So this is what I mean by an isobaric process, right? An isobaric process has to have that happen. So now I know that isobaric now implies that the pressure is equal to a constant. And if it's equal to a constant, then from the ideal gas laws, it says this: if I have a bigger volume, then I must have a higher temperature, because when I get to state 2, I'm going to have a smaller volume and therefore a lower temperature. So this isobaric process tells us 2 things. I expect that the temperature at 1 to be higher than the temperature at 2. I expect that the volume of 1 to be higher than the volume of 2. Now, the thing about this process is that there's a knife's edge type balance between these two processes. Because think about it, these two processes, to keep pressure equal to a constant. So the amount of work of the piston head adding energy must be compensated by the amount of heat flowing out of the piston. There has to be a balance. If it's not a balance, then we don't move at constant pressure. So now let's go to the second one here. So the second one, we're going from 2 to 3, and we're moving from along an isotherm. So here we go. So if I have an isotherm, then the process looks something like this. So now I'm going from 2 to 3, and this is isothermal heating / expansion. So again, there's two processes going on. There's working and there's heating. So when I say the word expansion, that means that there has to be work being done. So gas particles collide with the piston head to expand the volume. And what that really tells us here is that the gas particles decrease, because they got to give up the energy to the piston head, they decrease kinetic energy. So they're losing energy. But in order to keep this at constant temperature, there has to be heating. So now, to keep the gas at constant temperature, heating increases the kinetic energy of the gas particles. So one is decreasing it and one is increasing it. So now if I draw my picture as before, here's what I'm going to have here. So here's my volume and here's my pressure. So now what I'm looking at here is that I'm looking at this state here, which is 2. And now I'm going to go to my state 1, which is going to be, let's say, right here, to state 3. So now if I look at my path, remember if I say a path, it's a series of thermal processes, I'm going like this. So then what does my piston look like? So what I'm seeing here is that my piston's going like this. Starts here as a lower volume. And then when I come over here, it has a higher volume. So what I'm seeing here is that the expansion decreases the kinetic energy, because they got to give up the kinetic energy along this process here. And so the only way I can increase this, the only way I can increase the kinetic energy of the particles is that I have to have what? I have to have heat that now increases the kinetic energies of the gas particles. So now what you're seeing here is that I now have heat flow from my heat source, and it goes into the gas. Right? It goes into the gas. So when I'm looking at this, you could see here is that there is what? The pressure starts off high, and then the pressure decreases. It goes down. But the cost here is that I start off at a small volume, and now I get to a large volume. That's because the pressure is constant here. So then if I look at what do I mean by an isothermal, isothermal implies that the temperature is equal to a constant. And if it's equal to a constant, then it tells me that the pressure times the volume must be equal to the pressure of times the larger volume. A lower pressure, but a larger volume. So again, what do we expect? We expect here that P2 is going to be greater than P3. V3 is going to be greater than V2. Again, this process is a knife's edge, right? So there's a knife edge type balance between these processes to keep T equal to a constant. Because if it's not really balanced, then you can't have constant pressure. You can't maintain constant pressure. So now we're at our last one here. And when we look at our last one, we then have isochoric. And you could see here, so I'm going from 3 to 1, and I'm moving in a straight line at constant volume. So now if I come back here, I'm now going from 3 to 1, and this is isochoric heating. But in this case, there's no working. Why there's no working? There's no change in volume. So now I really only have heating going on. So if I look at my heating, what happens with my heating? Well, in order to increase the pressure, the gas particles have to be moving faster. So to increase pressure, gas particles must increase their kinetic energies to transfer more energy to the walls of the piston, right? You have to increase that. And the only way you can do this is that you have to increase temperature. So if I look at my graph now, I'm going from here, which is 3, and I'm going all the way up to 1. So you can see that my path is along this line. So if I look at this thing, my volume is fixed. Where I go from here Then I'm going to come up to here. So I'm going to fix my volume. Let's say I fix it to right here. That's my fixed volume. So then that means that the only way I can change the energy, since there's no work being done, is that I have to add heat. So now I have a heat source that's allowing heat to flow in. Right? So here's my heat. And this heat is what's increasing the kinetic energy. So in this situation, then, I have heat in. Heat flows into the system. So now, if I have isochoric, that implies that the volume is a constant. So from the ideal gas law, you'll see here is that the pressure at 3, the temperature, and the pressure at 3 have this ratio that must be a constant. But now if I increase this thing to 1, I have to have a higher pressure and a higher temperature. There has to be that balance. So then we expect that that P1 will be greater than P3. We expect T1 to be greater than T3. And that's what we mean by our isochoric process here. So what I want to do now is that I want to go on to B. So if I go to part B, we now want to calculate, now that we understand what's going on, we want to calculate all the pressures, volumes, temperatures for this thermal cycle. So let's look at our graph. So if you look at the graph, here's what our cycle looks like, our PV diagram. And what we first thing that we have to do here is that we need to put these into proper units. Okay, you got to put these into proper units. So here we go. Look at the pressure. It's in atmospheres. So the first thing that I'm going to see here is that note that the pressure at 1 is the same as the pressure at 2 because that's isobaric. So note that this is, I have to convert this to pascals. And you could see again that there's a cancellation. So then I get 5.05 times 10 to the 5 pascals. Then I look at my temperature at T1. T1, it says 300 degrees C, but if I add 273, I now get 573 Kelvin. And then the thing that I got to do last is I need to convert the volume. So that the volume of 2, it says that it's 10,000 centimeters cubed, but it has to be in meters cubed. So then I got to go 1 meter. And then this will be 10 to the 2 centimeters. So that's exactly 1. And then I got to cube that. And then I get 10 to the minus 2 meters cubed, or 0.01 meters cubed. So now I have everything converted. So now what I'm going to do here is that I'm going to set up a table. And let's look at the cycle to see what we know and what we don't know. So here we go. So now I'm going to set up a table. To organize the knowns/unknowns of pressure, volume, and temperature. So now if I look at my units, I know that my pressures are going to be in units of 10 to the 5 pascals. My temperature should be in Kelvin. and my volumes should be in meters cubed. So then I have state 1, 2, 3. So now I'm just gonna set up my table here. So you could see I have this. So what do I know? Well, I know that the pressure of 1 and 2 is the same here. So I could come in here and I could say that the pressure of 1 and 2 is going to be 5.05 times 10 to the 5, 5.05 times 10 to the 5. Another thing that we know here is that we know that the temperature at state 1, which is T1, and that's going to be 573 Kelvin. Okay. And the only other thing that I know is that I know that the volume at 2, so the volume at 2 here tells me that this guy is going to be 0.01 meters cubed. So what is it that I don't know? Well, the first thing here is that note that volume 1 and 3 are the same. So that means here, if I calculate the volume here, I know that this volume is the same as 3, and then 3 is the same as 1. So now when I look at the temperature, note that isotherm means that you have a constant temperature. So that means that the temperature at 2 must be at the temperature of 3. So if I calculate either of these temperatures, then we are there. And then finally, we do not know the pressure at 3. So what you're seeing here is that there are 3 unknown quantities that have to be calculated, right? So there are 3 unknown quantities. There are 3 unknown quantities. We need V1, we need T2, and we need P3. Okay, these are the guys that we want to do. Now, one of the things about this problem here is if we go all the way back up to the top, note that it tells us that we have 100 grams of helium. So the first thing I'm going to do here is that I'm going to calculate the number of mole. We are given that the ideal gas is 100 grams of helium. So this allows us, so now we can calculate the mole number. So let's go do that. So here is my, from the periodic table, I could see here that my mass here is 4. So here we go. So then this should be, N is going to be the mass of the sample divided by the molar mass of helium. So if I compute that, that means that I have 100 grams, and then the molar mass is going to be 4 grams per mole, and that gives us 25 moles for the value of N. So here's my thinking process now. My thinking process for calculating what was it? What are the 3 things? It's got to be V1, T2, P3. Goes along 2 paths. The first path here is that you use the ideal gas law approach. And the second process is that you use the ideal gas law conditions. Both are important to learn. And I'm going to take these and I'm going to do both just so you can see the difference. So here's my first path here. My first way of thinking here is I'm going to do the ideal gas law approach. So here's what I know. For a fixed gas, the mole number is always a constant. So then that tells me here is that the ideal gas law really says this here. It says that the pressure times the volume is proportional to the temperature. So if two state variables are known, the third can be solved for. In other words, if I have P1 and T1, then it allows me to calculate V1. So in this situation, what I'm going to do here is that what you want to do here is that you want to start by looking at the PV diagram and identify which states have two knowns. So let's look at that. So here's our diagram. So when I'm looking at this guy, what I want to pay attention to is that what is the pressure? Well, I know that the pressure is going to be in 10 to the 5 pascals. So I know that this is 5.05. And I know that the volume here is 0.01, where this is meters cubed. And I know that this temperature right here is 573 K. So I'm going to go through each of the states here. So if I use the ideal gas law, now look at state 1. Okay. So if I look at state 1, you see here is that P1 and T1 are known. So, but V1 is unknown. So that means I can apply the ideal gas. So now if I look at the ideal gas law, here's what it says. I know that it's P1 V1 is going to equal to NR T1. So now if I solve for the volume, you could then see that this is going to be NR T1 divided by P1. So then I just pick the stuff off the table, right? I'm going to take these values right off the table. And what I find here is that this now becomes what? I have 25 moles. My gas constant is 8.31 joules per mole times Kelvin. And then I have my temperature of 573 Kelvin. And then if I look at the pressure, it's 5.05 times 10 to the 5 pascals. So this gives me a volume of 0.263 meters cubed. But volume 1 and volume 3 are automatically known now. So I got one of my unknown variables solved for. So if I now look at state 2 here. So if I look at state 2, what do I know? I know the pressure, and I know that the volume are known. So then that tells me it's the temperature that I don't know. But according to the ideal gas law, I could now just solve the ideal gas law for this. So then the ideal gas law just tells me what? That the temperature at 2 must be P2, V2, and R. So if I plug in my values here, I'm going to get 5.05 times 10 to the 5 pascals times 0.01 meters cubed. And then I'm going to get 25 moles times 8.31 joules per mole Kelvin. And when I compute that number, I get 24.3 Kelvin, but that's the temperature at 2. But because of the isotherm, it's also the temperature at 3. But now, because I just solved for the temperature at 3, I now know 2 things at state 3 now. So if I look at state 3, I now know what? I know the volume at 3 because V1 and V3 are the same. And I now know the temperature at 3. So the only thing I don't know is that I don't know what the pressure at 3. This is unknown. So again, I'm going to use the ideal gas law. So if I now solve the ideal gas for the pressure, you could see here that I got to write P3 is then going to be nRT3 times the volume 3. Now, if I plug in all my values here, following the exact same process as we did before, I get 0.214 times 10 to the 5 pascals for P3. So now I've computed all 3 of these. So I'm going to take these guys and I'm going to copy this and bring it down with me. So now I could say that in summary, I could now fill in my table. And here's my table. So now if I just look at what I have here, look at my volume, it's 0.263. So now I'm going to take this guy out and this guy out. And I know that this is 0.263, 0.263. Look at my temperature now. I know my temperature for these two, which will then read 24.3 Kelvin, 24.3 Kelvin. And then finally, my pressure is then going to be 0.214 times 10 to the 5 pascals. So this is using the ideal gas law in order to understand this thing. Now, what I want to do here is that I want to outline a second process. And here I want to use the ideal gas law conditions. Now the ideal gas law conditions, this uses the ideal gas law conditions to solve for the unknown state variables. So that means here is that if I have an isobaric, isobaric implies that I have V1 T1 equals to V2 T2. If I have isochoric, this says that if I have P1 T1 P2 T2, and if I have an isothermal, then that tells me that P1 V1 equals P2 V2. There are some times when you have no choice but to use these. Now, what I'm going to do here is that I'm going to set up a slightly different problem now. Okay, so I want to be careful here. So to make this more relevant, I will slightly change this question. So it's not the same. And here's what I'm going to do. First thing I'm going to do here is that assume no mole number is given at all. So there's no way you can calculate it. And then the other thing I'm going to do here, I'm going to be given pressure 3. So pressure 3 from what we just calculated is this guy right here. So if I do that, then the PV diagram now reads like this. Okay, so now I have my PV diagram. So this is what it says here. I now know that this is still 10 to the 5 pascals. This guy is 5.05. I know this volume is 0.01, where this is in meters cubed. I know that this temperature is still 573 Kelvin. But the thing that's going to be given here that wasn't given before is that I know that this pressure is 0.214 10 to the 5 pascals. Now you might say, hey, I could still use the I-gas law. This condition here makes it impossible / very challenging to use the ideal gas law. So the point here is that you can't really use the ideal gas law unless you work yourself out. So what I'm going to do here is that I'm going to look at the ideal conditions. So what you're seeing here is that now my question goes like this. What is V1 and T2? Okay. That's what I really got to do. So what are the values of the volume and the temperature here? So the way I start to do this here is that I start by looking at the PV diagram and look at how each states are connected. So look how each state, look how each process connects two states. So if I look at state 1 to 2, which is an isobaric, then that means I have T1, V1, T2, V2. So then I have 2 to 3, because that's an isothermal, that's going to be P2, V2, P3, V3. And then if I look at my isochoric, I know that that's got to be P3, T3, P1, T1. So that means that if I look at these processes, 3 state variables must be known to calculate the fourth. So let's go look at that. So the first thing that I look at is that I'm going to look at state 1. Oh, no, not state 1. So I'm going to look at the process. I'm going to look at the isobaric process. So the isobaric process tells me that I connect 1 to 2. So when I look at that, what do I know about state 1 and 2? So I know the temperature of 1, and I don't know the volume. When I look at state 2, I don't know the temperature, and I don't know what's here. Let's just write it down. So the isobaric tells me this here. So you could see that I need T1, V1, T2, V2. So T1 is known. V2, these guys are known, but you're seeing that I have T2 and V1, they're unknown. So I can't solve for this. So this is impossible to solve. So now let's go to the isotherm. So if I look at the isotherm, this is the state that connects 2 to 3. So what do I know? So for the isotherm, note that I know pressure 2, volume 1, pressure 1. So that means here is that I know P2, V2, and I know pressure 3, they're known. So that implies that now V3, you can solve this. So if I now look at this thing, I'm going to use that condition. So then I see here is that if I solve for, so then from P2, V2, P3, V3, that tells me then I could then write V3 is the ratio of the pressures times the volume at 2. So if I can put this in, this will be 5.05 times 10 to the 5. This is 0.214 times 10 to the 5. And then I get 0.01 meters cubed. So all of a sudden I get 0.263 meters cubed. So now I know what the volume of 3 is, but the volume of 3 is the same as the volume as 1. So I now know 2 of the volumes that we didn't know before. Okay? So now that I have volume 3, now go back to the isobaric. So going back to the isobaric, look what I see now. So the isobaric tells me that now I know T1, I know volume 2, right? I know volume 2, and I now know volume 3. These are known. So that tells me now that I could now solve for the temperature of 2. So now I look at the isobaric condition, which then says T1, V1 has to equal T3, V3. So now, if I now solve for T2, T2 then tells me that it's got to be V2 over V1 times the temperature of 1. So then if I now start to look at the volumes, we just calculated one of the volumes, which is 0.263. And then the temperature at that point was 573 Kelvin. And when I compute that, I get 24.3 Kelvin, which then is the same as the temperature at 3. So now I've computed all of the unknown variables without using the ideal gas law. Two approaches for doing this.